In this video, I'm going to focus on collision types, as well as introduce the concept of momentum. Let's look at our collision types first, starting with the elastic collision. These are collisions in which the total kinetic energy before the collision is equal to the total kinetic energy after. And these are typically collisions where the objects do not stick together. Looking next at inelastic collisions, these are collisions in which there is a change of total kinetic energy from before to after the collision. And in these collisions, the objects typically do stick together. Know that in real life, collisions are almost always inelastic. This is because we expect other energies to be introduced when objects collide, other than just kinetic. Elastic collisions, on the other hand, are more hypothetical. They're for problem-solving purposes only. So if you're looking at a collision and it doesn't state which type it is, we should assume inelastic because that matches real life and represents the majority of collisions. Let's talk through a few sample collisions. Here we're looking at a blue cart moving to the right. It's going to bump into the stationary red cart. After the collision, observe that the carts did not stick together and they both move to the right. Breaking down the energy flow from before to after. Initially, I have a single moving object. That's the blue cart. And let's say the starting kinetic energy was 10 joules. After the collision, the blue cart is still moving. And let's say we calculate its kinetic energy to be 4 joules. So we know the red cart has kinetic energy after the collision because it's moving, but how much would it have? Here's where we focus on the fact that this is an elastic collision. We know elastic collisions are such that the total kinetic energy maintains its value, and therefore, since it was 10 joules initially, it should be 10 joules at the end as well. So 6 is the missing value, so it adds up to 10, and we're connecting elastic collisions to those that maintain the overall value of kinetic energy. Let's look at our next example. Similar start in a sense that we have a moving cart about to bump into a stationary one, but now observe that after the collision, the carts stick together and they move to the right as a unit. Breaking down the energies, I'll again use 10 joules initially, this time for the green cart, and after the collision, maybe we calculate the final kinetic energy of our two-cart system as 8 joules. So we see a clear decrease in our kinetic energies from 10 to 8. But where did that energy go? In real-life collisions, other energies are created within the colliding moment itself. Examples would be heat, sound, sparks. These are all things that take energy to make, but they're difficult to calculate and are often left out of our analysis. Rather, we're focused on the kinetic energies here, as dropping from 10 to 8. We remember that inelastic collisions are such that kinetic energy changes, so we can define this as an inelastic collision because of the kinetic energy change. Let's look at a second inelastic collision. Typically, we think of collisions as two separate objects combining into one, but in physics, we can consider a collision as one object that separates into two, like you see here. On the left, we have a purple and orange cart touching. They're both at rest. On the right, maybe an explosion has occurred between them. It sends the carts moving in opposite directions. Looking at our energy flow, on the left, we have energy stored in the explosion that is about to occur. This is a non-mechanical energy and would be very difficult to calculate. However, as this energy is used up, it creates two different kinetic energies, one for each of our moving carts. If we focus on kinetic energy, that value has gone from 0 to some. Kinetic energy has changed, and this would be another example of an inelastic collision. So let's summarize energy conservation and collisions. Note that the term elastic with collisions means that you can set the initial kinetic energy equal to the final kinetic energy. Otherwise, we'd expect the kinetic energy value to change, and this is the result of other non-mechanical energies being introduced in the colliding moment, things like heat and sound and sparks. These non-mechanical energies are complicated. There's some randomness to them, and they can't be calculated. So unless you see the term elastic with the collision, you should not attack it with energy. So if energy can't be used with collisions, what else can we do? We would need to introduce a new concept. This is known as momentum, and I'll define it on the next slide. Momentum, I'll define as how difficult it is to stop a moving object. So here we're looking at two football players that are in motion. Our goal is to tackle them and bring them to rest. Well, which would be more difficult to do that with? The big person moving quickly on the left, or the small person moving slowly on the right? I think we'd all rather tackle the small person, so we'd say that over here we have more momentum. Momentum is the variable lowercase p. We can calculate it as mass multiplied by velocity.